So this video is to introduce the idea of free versus dependent variables when talking about the equations of lines and planes. So here's an equation of a line. 2x plus 3y equals 6. We usually think about a line as an equation. So here, this is the equation of my line. So normally what we would do is we would solve for one of the variables. For example, I might try to solve for my variable y. And then I would get it isolated so that I get an equation. So here, if we thought about y, we solve for it by subtracting 2x from both sides. We get 3y equals 6 minus 2x. Now we could keep solving for y by dividing both sides by 3, and now we'll get y equals 2 minus 2/3 of x. What we've done is we've taken our equation for the line, we've turned it into a function interpretation. So there's a y-intercept at the point 0, 2, and we also know that we have a slope, right? The slope is negative 2/3, so if I go over 1, I go down 2/3. So this is one way of thinking about the line. For every x, I can find a value for y. So as we're going about this in linear algebra, we want to think about this in a different way. We want to think about y. Here we're going to call y our dependent variable, and we're going to treat x. Normally we would call that our independent variable. In the context of linear algebra, we're going to call that a free variable. So we'll call x our free variable, which is just a different way of saying an independent variable. Okay, so what I'm saying here is for each value of x, you can choose a value of x, and every different choice you make for x, you'll get a different value for y. So this is a function interpretation of the line. Okay, so what we're getting ready for now is we're getting ready to talk about a parametric representation of the same line. So instead of thinking about x as the independent variable and y as our dependent variable, we're now going to think about x and y as both being dependent on something. So we're going to represent a parametric curve where our point xy, x is going to be because it's a free variable, we're going to let it be represented by our parametric value or parameter t. T is just a typical choice because of the use of time. Once we know that the value of x is some parameter t, I use my equation, I replace the x with my parameter, and I get a formula y is also a function of t, so that I can write my parametric curve as a coordinate t, comma, 2 minus 2/3 t. So now, instead of thinking about y as a function of x, my point xy is a function of the parameter t. In linear algebra, we're going to be instead thinking about this from a vector perspective. That point can be thought of as being a displacement from 0. So if I thought about the point xy along the curve, I can represent that as a vector displacement from 0. And so the point xy we now think of as a vector xy. We're going to represent our vectors as these column matrices. We're just going to put in our parametric formulas. In the x-coordinate position, we're going to put the formula t. In the y-coordinate, we're going to put the formula 2 minus 2/3 t. Now the next step that we're going to do is we're going to think about how to rewrite this. And we're going to want to write it so that I have a vector of constants and a vector of multiples of t. So each of those formulas we're going to think about as being a constant plus a multiple of my parameter t. In the first coordinate, it's just t, and so there aren't any constant terms. We're going to represent that with 0, and t is being multiplied by 1. So we've expanded t to be 0 plus 1t. The second, the formula for y, it already is sort of written out, but we're going to explicitly think of minus 2/3 t as being adding a multiple negative 2/3 t. So now notice our formula now has a constant plus a multiple of t. And the way that vector addition works is I can think of that as being two different vectors being added together. I've got the vector 0, 2, and that's being added to the vector 1t, negative 2/3 t. Now, both of the terms in that second vector have the same factor of t. So I'm going to factor that t out, and so I get the vector 0, 2 plus the multiple t times the vector of the coefficients. And so I'll have 1, negative 2/3. So now this is my parametric representation in vector form. 0, 2 is a vector. And I can think of that as the vector that displaces from 0 to the origin to the vector, or to the point 0, 2. Okay, so that's a mistake. Let's fix that. I've got a vector 0, 2. Now, the second vector, 1, negative 2/3, is capturing the idea of the slope. Okay, so it's a direction vector. I go over 1, that's the horizontal displacement, and down negative 2/3. And so that's actually literally the slope vector. Okay, and the t just says I'm multiplying that direction by various values. So different values of t will put me at different points along that line. What we're going to be doing next is we're going to do the same idea, but now in 3 dimensions. Okay, so a single equation actually ends up representing a plane. So 3x plus 2y plus z equals 12 is representing this plane that I've visualized on the graph. Just like before, where we solve for one variable, in that example we solve for y, when there are 3 variables, when I solve, I get a single value is a function of other 2. This is going to create a surface. So here I'm just labeling the axes of the graph. So I've got the x-coordinate, the y-coordinate, and the z-coordinate. And traditionally, when dealing with surfaces, we think about z as a function of x and y. So z is going to be my surface height. For every x and y coordinate, I'm able to get that. So here, if I solve for z, I'll get 12. I'll subtract 3x to both sides. I'll subtract 2y from both sides. And now, given x and y, I can calculate a value for z. Okay, so here's a little illustration. If I imagine taking a point, for example, x equals 1 and y equals 1, I put those x and y values into my formula, I get a height, and that's how far above or below the xy plane I move to find the point of my surface. This is a function representation of that plane. I'm thinking about the surface as a function. So that's a mistake. Z is my dependent variable. Okay, so z is going to be my dependent variable. It depends on x and y. And this time there are 2 variables because the plane is a 2-dimensional surface. X and y, my independent variables, we call my free variables. Because I'm allowed to choose different values for x and y, and each choice I make for x and y gives me a different value of z. So now we're preparing for a parametric representation of the same plane. Because I have 2 free variables, I need 2 parameters. And typically, we will choose s and t. I count backwards through the alphabet. So x, my first free variable, will be s. Y, my second free variable, will be t. And now the z formula that we solved, we can write down 12 minus 3, the x value is s, minus 2 times y, and the y value was t. So now x, y, and z are parametrized by my 2 values, s and t. So I have a surface of points, x, y, z. So it's a triple. It's in 3-dimensional space. And it's represented by, in the x-coordinate is the parameter s, the y-coordinate is the parameter t, and in the z-coordinate is 12 minus 3s minus 2t. So there's these 2 dimensions, these 2 free variables that allows me to spread out into 2 different directions. We want to think about this in a vector representation. So just like before we had x, y, this time we're going to write a vector displacement to the point x, y, z. Okay? And we're going to write my 3 parametric formulas. S for the x-coordinate, t for the y-coordinate, and 12 minus 3s minus 2t in the z-coordinate. And just like before, we want to think about each of those formulas as a number plus a multiple of s plus a multiple of t. Okay? So I'm going to rewrite, if it's not there, it's going to be 0. So we have, in the x coordinate, I have 0 plus 1s plus 0t. Okay, so the constant and t term didn't exist. We introduced zeros there. In the second coordinate, the y coordinate, we have 0 plus 0s plus 1t. And in the third coordinate, we have 12 plus negative 3s plus negative 2t. Okay? Now notice this time we have 3 terms. I've got a constant term, I've got a multiple of s term, and I have a multiple of t term. So we're going to write this as a sum of 3 different vectors. We'll get the constant vector with 0, 0, 12. I have s is a s is a multiple in that second spot, so we'll factor it out. S times the vector 1, 0, negative 3. And then I'll have the third column, I have t is a multiple times the vector 0, 1, negative 2. So now I have these 3 vectors. And what that represents here is 0, 0, 12 is a point on the plane. So I think I should actually be drawing that here pretty soon. We're going to draw the vector from the origin. I think I changed color because purple blends too well with the plane picture. So I take the displacement vector from 0, 0, 0, the origin, to 0, 0, 12. I'm going to call that a point on the plane, or here we're going to call that a particular solution or a particular point. And then the other 2 vectors that we have s and t being multiples of are going to be 2 direction vectors on the plane. Okay, those are going to correspond to, in Calc 3, those are going to be related to like tangent vectors. Okay, so in the 1, 0, negative 3 says if I go 1 unit in the x direction, I go down 3 units in the z direction. So that green vector is supposed to be capturing that idea. The second vector is 0 displacement in the x direction. 1 displacement in the y direction corresponds to a negative 2 displacement in the z direction. So if I go 1 unit in the y direction, my graph should drop down 2 units in the z direction. Okay, so it's hard to see in 2 dimensions what those are. And I think here I try to drag the, we're going to in a moment go to the 3D calculator tab in the browser, which is illustrating this. Okay, so 0, 0, 12 is a particular point on the plane. And I didn't say fixed because that's going to have a different meaning when we get to differential equations. So we have our particular point, or a particular solution. That's my displacement to the plane. And then I have 2 direction vectors. And those 2 direction vectors allow me to spread out or span the entire plane. All right, so here what I'm going to be doing is I'm going to be adding the vectors to the graph. And unfortunately, the 3D response was sort of staggered. So there's my particular solution. The vector 0, 0, 12 goes from the origin up to the plane. And here I was just trying to get it so you could see that there's the plane I'm actually displacing up to that point. And now what I'll be doing is I'll be adding vectors for my 2 direction vectors. And I don't, by default, GeoGebra puts a vector with its tail anchored at 0, 0, 0. And so in order to push it up to be at that point that we created at 0, 0, 12, I'm going to translate my vector so that it's anchored at that point. So here we're going to translate the vector, and our first direction vector was 1, 0, negative 3, and we're going to anchor that to the point 0, 0, 12. Okay, so that's a vector, and it's actually one direction in the plane. I'm just here trying to change my colors so that it stands out. So that's one vector. That vector we're trying to show is in that plane. Okay, so then we're going to add the second vector here in just a moment. our second vector we also want to add. So we're going to translate our vector, and this time it's the vector 0, 1, -2. That's my displacement vector, and we want to anchor it to that point 0, 0, 12. Okay. And so there's that second vector. And again, just the graphics weren't going fast enough. I think my computer had the same thing that was causing my audio issues was causing staggering on my browser. I didn't realize it at the time. But those two vectors give me two directions in the plane. So from that point 0, 0, 12, those two directions, if I follow them, they stay inside the plane. And every point in the plane I can get to by starting at 0, 0, 12 and then following each of those directions some particular amount. So this is going to be a key idea for us as we solve our systems of equations. We want to be able to think about the dependent variable. We can solve for it in terms of my other variables, and then we can represent it parametrically in terms of these free variable parameters. And that allows me to capture all of the different points on either the line or the plane. All right, I apologize for the audio issues that we had, but hopefully that worked reasonably well. Good luck.